Two things should be particularly interesting for the participants of this conference, namely the part concerning computation of eigenvalues of some sequences of matrices given by some very simple recurrence rules, or if you want spectra of random walk operators on self-similar graphs. So it's very well known, the relation between additive combinatorics and estimates and computing spectra of random walks operator on some families of graphs related to groups, or if you want some expansion properties for such graphs. And another thing are the box ball systems, which are related to some problems in number theory. So let me start with some references. So first of all, there is an old joint work with Tsuyoshi Kato and Satoshi Sugimoto, on box ball systems and automata. So it appeared in Communications in Mathematical Physics. It's 2017. And there is a more recent paper I wrote under the title From Partial Differential Equations to Groups. So it's a chapter in a book published by Cambridge. So actually, I received the book last week. So indeed, I would like to present, hopefully, which is a very general way of associating to partial differential equations countable groups, finitely generated groups. And important ingredients in this construction is really considering these ultra-discrete versions of these equations and relating them to groups by considering random walks on solutions to these equations. But I think it might be interesting for you to see it, how it relates to other topics, namely to physics. Maybe also I'll show a connection to some invariants, topological invariants of closed manifolds. So we will start here with our example of a PDE will be a Kordevec equation. We will consider its ultra-discrete version, which is a box ball system. And by considering random walks on the solutions to this equation, we will obtain a group. In this case, the random walk on the solutions to this equation will correspond to the random walk on the Lamplighter group. Okay, so let us start with the Kordevec-de Vries equation. So we consider a function of two real-valued function on two variables, x and t. This is supposed to be time, and I write it in the most classical version that probably most of you seen, namely that derivative with respect to time plus 6 times u spatial derivative plus the third derivative with respect to x is equal to 0. So it's supposed to describe the waves, historically the waves in the shallow waters of Amsterdam canals. Discrete versions of PDEs are obtained as follows. You replace derivative by finite, by the difference of the values. So the function in the discrete setting is defined only for on integers, and the derivative corresponds to the difference on the neighboring integers. So formally, you can get the continuous version by replacing here 1 by epsilon and dividing our expression by suitable powers of epsilon, and in the limit you will get the continuous version. Now in the ultra-discrete version, so that's what we will talk about, the function will be defined, so noted by v, only on integers. So x is replaced by integer n times, say, we'll denote again by t, but this time is discrete. And what is also important that the function will not take real values anymore, but only finite number of values, say 0 and 1. So, and this is formally obtained, well, this ultra-discrete limits by taking the limits in the sense of tropical geometry. So let me describe these solutions to this equation, maybe using the language of this box ball systems. So for a given time, such a function on integer which takes values 0 and 1 can be described as a configuration of balls in boxes. So we have a line of boxes labeled by integers. Say function has finite support. It takes only finitely many ones. So this can be described as putting finitely many balls into these boxes. Okay, so suppose, well, if you have function which is say 0, 0, 1, 1, 1, 1, 0, 0, it can be described as this configuration of here 3 balls and 1 ball here, and then empty. If it's then a sequence of zeros, then there are only empty boxes. So this is the configuration at time t. What will be the configuration at time t plus 1? So I'll use the description with the so-called carrier. So the carrier will move from left to right and will start picking up the balls and then putting them into empty boxes. Okay, so we start from the left. Here is the first ball. So the carrier picks it up, then the second one, then the third one. So here we have 3 balls, and we start to drop them into empty boxes. So we drop the first one, second, we still hold one. Now we pick up this one, and then we drop it to this box and to this one. Okay, so it's at the time t plus 1. Pardon? So we pick up this ball, and we cannot drop it here. Yeah, there is a ball, so we have to pick it. We start dropping the balls when we see the first empty box. Okay, in each box you can have at most one ball. It's a function which takes values 0 and 1. So either it's empty or there is a one ball. Okay, pardon? Oh, okay. Yes. Thank you very much. Thank you very much. Thank you very much. This was right. Excellent. Very good. Very good. So maybe we'll do one more iteration. Okay, so that we're. Okay, so we pick up this ball, this one. We hold two balls. We drop this one, the one ball in this empty box. We still hold one. We pick up this one. So now we hold 3 balls, and we can drop them into this empty boxes. And actually now it's easy to see what will happen in the future. At each iteration, this one ball will move by 1 to the right, and this packet of 3 balls will move by 3 to the right. And also, you can imagine what it looked like in the past. So you had this packet of 3 balls moving very fast to the right. Okay, this one ball moving slowly to the right. At some point, there is an interaction, and again, you have these packets moving to the right with different speeds. So it looks like a soliton solution to the KdV equation, right? You have these 2 waves moving with different speeds, and at some point they interact, and then in the future again you will see this waves moving with different speeds. Okay, so actually there is some heuristic why it's related to the KdV equation, but as I said, it can be formally deduced using the limit in the sense of tropical geometry from the discrete version of the KdV equation. So actually, maybe a useful exercise for you would be actually to write an equation for this function b, solution that would satisfy that would be given in this way. So maybe the hint is, so here the function takes only values 0 and 1. So the algebraic operations that you should use is the maximum and addition. Okay, this corresponds to the fact that when you take these limits in the sense of tropical geometry, well, also you change algebraic operations. So plus becomes maximum, and multiplication becomes addition. Okay, but I think this description already gives you a lot of intuition concerning this equation. No. Its coefficients are not important. This is like the standard way of writing it. Okay. So next step in this construction we're going to see is actually associating automata to this picture. And for this, I will also introduce one parameter called capacity. So let K be a capacity. Okay, so namely, we will impose that the carrier at the given time can hold at most K balls. So if we already picked up K balls and we see another box with a ball, we do nothing. We just pass to the next box, and if it's empty, we can start dropping. And once we carry less than K balls, we can start picking up new balls again. And this can be described by a finite automaton. So the states of the automaton will correspond to the number of balls we hold. So let me draw this automaton in the case when the capacity is equal to 1. Okay, so it looks like a very, maybe even too simple a case to consider, but it's already interesting. So at the given time, we can hold at most one ball. So we have two states. There is a state, say A0, so it means that we don't have any ball, and there is a state that we label A1. So here we hold one ball. So if we don't have any ball and the input is 0, it's empty box, like we do nothing, right? So the input is 0, the output is 0, and we go back to the state A0. On the other hand, if the entry is 1, so there is a ball, because we had none, we can pick it up. So the input is 1, output is 0, and now we are at the state A1. We hold one ball. Okay. If we hold one ball and the box is empty, so the input is 0, we can drop this ball. Okay, so the output is 1, and again we are at the state A0. And finally, if we are at the state 1, input is 1, we cannot pick up this ball because the capacity is 1, so nothing happens. Output is also 1, and we are back to the state A1. It's very easy. You can imagine a similar automaton for arbitrary capacity. However, realizing this as an automaton, it's a crucial step in connecting it to a group. So let me explain this construction. So by the way, it's a very general construction how to an automaton under some conditions associate a group. Like if you would like a very easy to read reference about this theory, so I wrote Bourbaki seminar on this construction on so-called automata groups. Let me explain how it should go. So we will consider now the sequences of zeros and ones. Which start somewhere, and then they are infinite to the right. And if you start at the state A0, you obtain transformation function from such sequences. So namely, for instance, if you are at the state A0, the input is 0, the output is 0, so you have 0, and you go here to the state A1, so to the state A0, and you repeat, you follow the diagram to compute this mapping. One could also start at the state A1, and if both mappings are invertible, you can define a group generated by this mapping A0 and A1. And surprisingly, very simple automata can lead to highly non-trivial groups. In our case, these mappings are not invertible. So we will have to, using this construction, we would only obtain a semi-group. So in order to obtain a group, and also it might be seen as a part of this more general way of obtaining groups from semi-groups, we will consider the random walk on the solutions to the BBS, and this is done as follows. So actually, we can first let us consider finite sequences of zeros and ones of length n. Okay, and these mappings let us denote as A0n. Okay, so this is if we started at the state A0, and A1n if we started at the state A1. Okay, so in this way we have these two mappings. Now let us describe them using matrices. So we have 2 to the n sequences of zeros and ones of length n. So let us label them from 1 to the n, and the mappings will be described by permutation like matrices. Namely, you will put at the entry ith/jth1 if the ith sequence is sent onto j sequence. If our mappings are given by a finite automaton, we have recurrence rules. So for instance, A0n plus 1, this matrix can be decomposed into blocks as follows. So suppose that labeling was such that first we put to the n sequences of length n plus 1 which start to 0, and then remaining 2 to the n sequences which start with 1. So if we have a sequence starting with 0, and we are at the state A0, the output is 0, and we are back at the state A0. So in other words, here would be matrix A0 n. On the other hand, if the input was 1, okay, the output is 0, and we go to the state A1. So here, as a block, we would find the matrix A1 n, and here would be 0 entries. Okay, and in a similar way, for A1 n plus 1, we can decompose it into blocks. So if we are at A1, if the input is 0, the output is 1, and we are at A0. So here would be A0 n. And if the input is 1, the output is 1, and we are again at A1. So here would be the matrix A1 n, and here we would have zeros. Okay, so that's a very simple recurrence rule concerning this matrices. So actually here it's very clear that they are not invertible. Okay, that they would not. You cannot define a group by looking at the action. So what we going to consider is this random walk operator. So namely, we will take the sum of these matrices and their transposes. And to use probabilistic language, so let us divide it by 4. So let us consider the matrix, which is the sum of A0 n plus A1 n plus A0 n transpose plus A1 n transpose. Okay, so this is the matrix Mn. What is important that it's a bistochastic matrix. That the sum of lines and columns is equal. It's equal to 1. Okay, it's not always the case. It's always the case if the if this matrices would be invertible. If we could already define the group as we said at the beginning. So there is some condition to check. That for some automata, even if they only generate semigroups, not groups, under some conditions, this matrices would be bistochastic, which is indication that we are close to the invertible case, to the group case. And as I said in the beginning, at the introduction, we'll be able actually to compute all the eigenvalues. We'll get complete spectral information about the sequence of matrices. So we'll compute all the eigenvalues of this matrices using this recurrence rule. So namely, one wants to obtain recurrence on the level of the, so let us write the function f n to be determinant of mn minus lambda identity matrix. Actually, to obtain this recurrence relation, one has to, in all the situation when this kind of computation can be carried out, one has to introduce here yet another sequence of matrices, so that would one obtain, and this depends on the situation. So one really needs to consider a function of two variables, and then one can prove that phi n plus 1 of lambda mu is obtained from phi n by applying a rational function to lambda and mu, and really from by studying the primitives of this function, one can obtain all information about all the eigenvalues. And the property that is important for these mappings is that, well, so phi is the map from R2, is the rational map from R2 to R2. What is important that there is a rational projection onto R such that this map factors by a polynomial. Okay, so there is this link to integrable dynamical system. So let me now describe the eigenvalues for these matrices. Actually, let me do it description will be, to save time, I'll give the asymptotic information about the spectrum. So for the eigenvalue lambda, we'll define the limit multiplicity as follows. So we count the multiplicity of lambda among all the eigenvalues of this matrix. We'll define it by the size of the matrix. Okay, so by 2 to the n, and we'll take the limit when n tends to infinity. In general, this limit does not have to exist, but in this case, it does exist. And here is the result. So the only eigenvalues that appear as eigenvalues of these matrices are of the form cosine pi p over q and the limit multiplicity so suppose P and Q are relatively prime. So the limit multiplicity will be 1 over 2 to the power Q minus 1. Actually, already the fact that the limit is not 0 is interesting, that this multiplicity grows proportionally to the size of matrices. And actually, what is maybe more surprising, that for any non-trivial eigenvalue, which appears for some n, this limit multiplicity is non-zero. Okay. Actually, when you sum up all these multiplicities, so you have to sum up as many times as there are integers relatively prime to q. So it's Euler function phi of q divided by 2 to the power q minus 1. This is equal to 1. Okay, so this is already established by Euler. Okay, so it's actually interesting that such a simple recurrence rule, maybe it's the simplest possible non-trivial recurrence rule, leads to quite a non-trivial sequence of matrices from the spectral point of view. And one can, for each of them, one can compute exactly the eigenvalues and the multiplicities. And here is just information about asymptotics of the spectrum. Okay, excellent. So now, but actually we started at 3, so there is. Couple more minutes. Okay, great. So maybe. Okay, so maybe what would be important to mention in this context is actually that this limit multiplicity appears computing some topological invariance of closed manifolds. So let me very quickly say about L2 Betty numbers. Which were defined by Atiyah. Okay, so the setting is the following one. We consider a closed manifold. Okay, with the fundamental group gamma, and I'll give you definition in the case when it's residually finite, where we will be very close to the situation. We will have this finite approximations. So we have a sequence of finite index normal subgroups of gamma. Okay, suppose it's also that it's descending, and that the intersection is identity. So now the ith L2 Betty number of this manifold can be computed as follows. You compute usual ith Betty number for the finite cover of this manifold corresponding to this subgroup gamma n. So it's a universal cover divided by the action of gamma n, and we divide by the degree of the covering. So this is the index of gamma in gamma n, and we take the limit when n tends to infinity. So the usual Betty numbers can be computed by the kernels of some operator, which actually in this setting might be a random walk operator on finite quotients of groups, and dividing by this index exactly corresponds to as here the size of this metric of the approximating sequence. And so to finish, let me give you the group. So the group will be the Lamplighter group, which has easy algebraic description. Namely, it's the direct product of Z mod 2 over Z, semi-direct product with Z, where Z acts on the basis by translation. So the natural generators for this group would be a generator for integers. So let us denote it T, and the generator for one copy of Z mod 2. Let us denote it A. And now, if you consider the following set of generators, T inverse, A T, and A T inverse, if you consider the random walk with respect to these generators on finite quotients of this group, it corresponds exactly to this random walk. You obtain the matrix which is conjugated to this matrix. So indeed, we can interpret it as a random walk on a group, random walk on the solutions to the ultra-discrete version of the KdV equation. Okay, thank you very much for your attention.
Thank you very much. Is there one good question again? Because we are again a little bit late. So if there is on the chat, you can type now if there is in person. Yes, there is. Okay, wait for the mic.
Just a very naive questions with respect to the first model. Can you put several stones on one? Can you put 2 stones on one square? You had no stones, a stone, a stone, a stone, nothing. Can you make some piles? I mean,
right. So what I described is really the simplest box ball system, and it's a theory on its own. And indeed, you can use, you don't have to make this restriction that there is only values 0 and 1. There are many variants. It's
So you're saying that you can relate these automata groups and manifolds, and fundamental groups of manifolds.
That's right. So here, maybe there is one comment I didn't have time to explain. So when we talk about manifolds, the fundamental closed manifolds, the fundamental groups are finitely presented. The Lamplighter group, this group is not finitely presented. However, it embeds into a finitely presented group. This follows, for instance, from the Higman embedding theorem. It's a recursively presented group, so it's a subgroup of a finitely presented group. And then, if you consider the same, well, the random walk operator or element in the group algebra. So let me write it. So as an element of the group algebra, we will consider 1/4 t plus t inverse plus a t plus a t inverse. And now, if you look at the action of A on L2 of the group gamma, okay, so you take the sum of the translation by these generators and you divide it by 4, you obtain that this operator has the following eigenvalues, okay, and this limit multiplicity, it's also can be defined as the von Neumann dimension of the corresponding eigenspace.
Okay,
so
Andrzej,
now
I won't pretend I understand.
Yes,
but
just to finish, because to relate to your question. So now this group gamma, if this is Lamplighter, it embeds into finitely presented. Finitely presented group. It can be even written explicitly.
Oh, yeah, that's.
It can be written explicitly, okay. And but now, if you this operator A can also act on this finitely presented group, okay? And this the spectrum is exactly the same. It's exactly the same. The same eigenvalues and the same limit multiplicity. The same von Neumann. This is a property of the von Neumann dimension, that it doesn't depend. So this computation can be really translated into a computation about the finitely presented group, and any finitely presented group can be realized as the fundamental group of the closed manifold, and one of its L2 Betty numbers, there is construction of such a manifold that, for instance, third L2 Betty number would correspond to the limit multiplicity of 0, of the eigenvalue 0. Okay, so any computation you do for this random walk operator can be translated into computation about this L2 Betty numbers of closed manifolds.
Well, I'll catch you after dinner.
That's why I wanted to stress that this is really fundamental. That's how you compute this L2 Betty numbers. It's really by computing kernels of this random operator. So there is no restriction. If you have a finitely presented group, any element in the group ring can give rise to a manifold with one of its L2 Betty numbers, which is exactly the von Neumann dimension of this kernel. It's really important.
Well, thank you very much. So if there are any more questions, you can ask them at the coffee break, and we'll thank Andrzej again.